Hello again. We're continuing looking at the calculations involving heat energy questions. And what we're doing now is looking at question 2, and we just did question 2a, so we're just going to question 2b. It says, assuming all this energy is transferred to heat energy when it hits the ground, calculate the rise in temperature of the lead. What assumption have you made? So, first of all, we have to consider which formula we're going to use. So we rearrange the formula for specific heat capacity. So we use delta theta equals delta Q divided by MC. Substitute in, we get 122.5 divided by 0.5 multiplied by 30. This gives us 1.88 Kelvin. So this is the temperature change. And here we're assuming that all the energy is converted to heating lead. Now in reality that's not going to be the case because some of the heat will be transferred to its surroundings and not into the lead. Question 3. A car of mass 1,000 kilograms travelling at 72 kilometers per hour. Note that that's not an SI unit. The SI unit would be meters per second. So 72 kilometers per hour is brought to rest by applying the brakes. Assume that this kinetic energy becomes transferred to the heat energy in the iron brake drums, which have a total mass of 20 kg. Part A, show that 72 kilometers per hour equals 20 meters per second. Now with a show that question, you need to show as many steps as possible. So in this case, we would write there are 60 times 60 equals 3,600 seconds in 1 hour. So we're showing, first of all, that we understand that we need to convert the seconds into 1 hour. We need to convert the hours into seconds, and in order to do that, we need to consider this relationship here, that there's 3,600 seconds in 1 hour. Therefore, 72 kilometers per hour is 72,000 meters divided by 3,600 seconds. Note, it's meters divided by seconds. If we divide the meters, the number of meters, which is 72 kilometers, 72,000 meters, divided by a number of seconds in 1 hour, because per hour means every hour, just 1 hour. This gives us 20 meters per second. Part B, calculate the temperature rise in the brake drums. So the kinetic energy is half mv squared, half times 1000 times 20 squared. Again, we do formula, substitution, answer, unit. Formula, substitution, answer, unit. This gives us 200 kilojoules. So in your calculator, if you put this in, you would get 200,000. So that would be 200,000 joules, and so that's 200 kilojoules. Once we have the kinetic energy, we assume that all of this kinetic energy again goes into heating up the substance. In this case, increasing the temperature of the brake drums. So delta theta equals delta Q divided by MC. So we get 200 kilojoules divided by 20 times 460, and this gives us 21.7 Kelvin. Question 4. A 5,000 watt immersion heater is used to raise the temperature of 10 kilograms of water from 20 degrees C to 60 degrees C. What time will be taken to do this, assuming no heat is lost, I should say, to the surroundings? So the energy required is delta Q equals MC delta theta equals 10 multiplied by 4200 times 40, giving 1680 kilojoules. The time is energy divided by power. That's your formula. Rearrange from power equals energy divided by time. So energy is 1680 kilojoules as just calculated, divided by a power of 5,000 watts. it gives 336 seconds. Note that if the power was more, then the time taken would be less to deliver this amount of energy. And if it was less, if the power was less, then this time taken would be longer to deliver the same amount of energy. So it makes sense. Question 5, part A, define what we mean by the specific heat capacity of a substance. So specific heat capacity, SHC, is the heat energy required to raise 1 kilogram of a substance by 1 Kelvin in temperature. 5b, a 1.0 kilowatt heater takes 7 minutes 6 seconds to raise the temperature of 20 kilograms of a metal from 20 degrees to 60 degrees C. Part 1. If 25% of the heat supplied by the heater is wasted to the surroundings, calculate the heat absorbed by the metal. So if 25% of the heat supplied by the water is wasted, then that means that 75% of the heat is absorbed by the metal, i.e. it's gone into what we call useful energy. Useful energy is just what the energy that we're interested in whatever case we're looking at. So the energy supplied in this case is the power multiplied by the time. So this is 1000 watts multiplied by 426 seconds, which gives us 420 kilojoules. So of that energy which is being supplied, that's the total energy being supplied, we now need to find what 75% of that energy is, and that is 315 kilojoules. So that is the amount of energy that is transferred to the metal, okay, or absorbed by the metal. Part 2, calculate the specific heat capacity of the metal. So specific heat capacity is found by rearranging the formula, delta Q divided by m delta theta, so that's the formula we're going to use. Delta Q in this case is the energy that's being absorbed by the metal, because we're not interested in the other 25%, the other 25% has disappeared to the surroundings and is not being used to heat up the metal. So in our calculation, we don't have to consider that. M, the mass, is 20 kilograms, and the change of temperature is 40, so that's 60 minus the 20, you see. So if you put all that into our calculator, you should find that you get 390 joules per kilogram per Kelvin, which is the standard SI unit for the standard unit for specific heat capacity. Question 6. A copper cylinder of mass 0.1 kilograms was raised to 100 degrees C and added to 0.15 kilograms of paraffin, initially at 11 degrees C. After stirring, everything reaches a final steady temperature of 20 degrees C. Assume all the heat is lost by the copper is transferred to the paraffin without any being lost to the surroundings. A, calculate the heat lost by the copper as it cooled. Again, formula delta Q equals mc delta theta equals 0.1 multiplied by 390 multiplied by 80. Now this is the heat lost. Now this is 3,120 joules. Part B. How much heat is gained by the paraffin? The heat gained by the paraffin is equal to the heat lost by the copper. Okay, so the heat's going from the copper to the paraffin. So that's the same. So we're assuming all of it lost by the copper goes to the paraffin. Calculate the specific heat capacity of the paraffin. Rearrange the formula, delta Q divided by m delta theta. We get 3,120 divided by 0.15 multiplied by 9, which gives 2,310 joules per kilogram per Kelvin. Question 7. 20 grams of ice are heated from minus 18 degrees C until it becomes steam at 100 degrees C. By adding up the energies needed at each of the stages of this change, calculate the total energy required. So I've just sketched a little graph here. When you sketch a graph, you put in the axes, you label the axes, and then you just put in points values here which are important, the important values. And note, it doesn't have to be to scale, sketch graph, so never to scale. You just put in the numbers which are important. It's also important to put some units in, so this will be degrees centigrade here. This will be joules. Okay, I've not put the unit in there, but in this case, it's where we know we're working in joules, and we're focusing on the values of the temperature. So we know from the question it's heated from minus 18 degrees C. So we put that minus 18 in there. And we use the sketch graph to help visualize what's going on, because there's quite a lot of information in the question. So it goes up, okay, uniformly. It will go up. If you've ever done an experiment in class, you'll find this. Okay, it'll go. This is what's called a heating curve for water. So the ice here, it's ice until it gets to 0, and then there's some energy that's required, which is called the latent heat energy, in order to melt it. And then it gets to a point where once it's all melted, the temperature goes up again when more energy is put in. Then it reaches 100 degrees C and more energy is required to be put in, but as it's boiling. So this point is where it's boiling, and then when it's all boiled, if you keep on adding energy, then the temperature of the steam will then increase. So what we have to do is you have to add together all these little bits, the energy that required for all these parts of the heating. So when it's ice and when it's changing temperature, we have to use this equation, delta Q equals mc delta theta, when it's changing temperature. So if we calculate the amount of energy that we have going in whilst it's ice, whilst the ice is being warmed up, then we use this equation. We get the mass is 0.02 kilograms, multiply the specific heat capacity and the change in temperature from minus 18 to 0. That's a change of 18 degrees. So we get 756 joules. Then when it gets to this point, it's now not changing temperature, but we need to consider the latent heat of fusion of ice. So this is the energy required to completely melt all of it once it's got to 0 degrees. So we use this different equation, which was back the second equation here. And if we put in the numbers, we get 0.02 times 3.36 times 10 to the 5 equals 6,720 joules. When it's water, it starts to heat up again, so we go back to the first equation. It's changing temperature, so we calculate that. We get 8,400 joules. When it gets to the 100 degrees, now it's starting to boil, but it requires that amount of energy to boil because of the latent heat of vaporization of water. So we have to use the second equation. We add all that up. We calculate that. We get 45,200 joules. And so if we add all of these delta Q's up, 1, 2, 3, 4 of them, we sum them up, the sum of the energies, and we get 61,076 joules. So that is the whole amount of energy required to warm the ice, melt the ice, warm the water, and boil the water to make steam. So that's your question number 7. Question 8. Why are pieces of ice at 0 degrees C added to a drink at room temperature more effective at cooling it than an equal mass of water at 0 degrees C? Simply speaking, GCSE you could write because ice has a lower specific heat capacity than water. Question 9. A. Define the specific latent heat fusion of ice. So the specific latent heat of ice is the heat required to melt 1 kilogram of ice, or that energy given out as 1 kilogram of water freezes. (9b) A fridge can convert 400 grams of water at 20 degrees C to ice at minus 10 degrees C in 3 hours. Find the average rate of heat extraction from the water in joules per second. So the heat extracted in 3 hours is the same as you have to work out the cooling of water and the conversion to ice and the cooling of the ice. So it's just like in this graph here. Okay, you've got the cooling of the water. It's going the opposite way now. So you cool the water, you convert it to ice, and then you cool the ice. So if we work that out, we've got the mass times specific heat capacity times the change in temperature plus the latent heat of fusion of ice plus the cooling of the ice. So the cooling of the water, this term here, the freezing of the water, this term, and the cooling of the ice. So we add those three together, you'll see that we've got the first equation, the second equation, and the first equation again. So substitute into the first equation, substitute into the second equation, and substitute back into the first equation again, this time using the values for the ice. So we get three values for the heat. We get one for the heat loss cooling the water, one for freezing the water, and one for cooling the ice. And the total sum is 176,400 joules. The power equals energy divided by the time, which is 16.3 watts. And lastly, question 10. 10a, define the specific latent heat of steam. So the specific latent heat of steam is the energy required to convert 1 kilogram of water from liquid to steam. Okay, so specific latent heat of steam, that is. Part B, a kettle with 1000 watts element contains 1.5 kilograms of water at 20 degrees C. How much heat is needed to bring it to its boiling point? So for this, we're thinking about heating the liquid water, and so it's changing the temperature. So we don't have to consider anything to do with the actual boiling into steam, the energy required for that. It's just to raise it to its boiling point. So it's the change of temperature. So we use equation number 1. So this is mass times the specific heat capacity multiplied by the change in temperature. So this gives 504 kilojoules. 10b, a kettle with 1000 watt element contains 1.5 kilogram water at 20 degrees C. How much heat is needed to bring it to its boiling point? So here, C, how much heat is needed to boil half of this water away? Mass divided by 2, which is half the water, is 0.75 kilograms, and then you have to do because you're talking about boiling and not changing the temperature, we have to use the second equation, which is delta Q equals ml, which is 0.75 kilograms by 2.26 times 10 to the 6, which gives 1,695 kilojoules. Part D, if all the heat from the element goes into the water, calculate the time taken to bring this water to the boil from 20 degrees C. So again, we're thinking about using this equation, time equals energy divided by power. So the time to start boiling is the amount of energy, which you calculated in part B, divided by the power, which you're told is 1000 watt element. That gives 504 seconds, which is 8 minutes 24 seconds. And then finally, the time which is then taken to boil half of it away is the total here, the total energy for half of it to boil divided by its power. So that's 1,695 seconds, and this converts to 28 minutes and 15 seconds.